Okay, hello everyone. Sorry for the technical difficulties, and welcome to Starry Nights Live. I guess we'll be on a little bit of a rush schedule tonight because it took us 15 minutes to figure out something was wrong with our YouTube channel. So
Yeah,
anyway, my name's Kieran. I work at the Trottier Observatory as a technician and Starry Nights staff. If you look in the top corner of the screen, you'll see the telescope. It's my job to keep it running, and
you're
surprising
not doing a
amount
very
of
good
work.
job.
Yes, and I love to use it to look at the stars, and so does everyone else, including Malcolm. Malcolm, I believe
Yeah,
you
that's
recently
me.
officially became an astronomer. Is that true?
No,
No?
maybe.
Yeah, aren't you talking to the public or to a group of other astronomers about your own astronomy sometime soon?
I am. Yeah, I am talking to a group of astronomers about my astronomy soon.
Oh, so he's
That
officially
was
got his
not that
astronomy
was not
license.
correctly worded. There's there's no such thing as an astronomy license.
So what are we looking at right now? Well, these two dots, you can notice they're different colors. These are actually the stars. Well, the star system Albireo.
I
Oh,
can tell you what they're not. They are not an astronomy license.
that's true.
Yeah.
So Albireo is in fact it's a double star. You can see that one is a different color from the other, and they're also different temperature. And what you might not know about our beautiful galaxy is that most of those dots you see out there in space are actually not single stars like our lonely sun. They're often binary systems or even triple systems. That means the suns orbiting each other, stars orbiting each other, kind of like our planets orbit our sun. Most of the dots, if you go outside and look out the window right now, most of those are not single stars. Single stars are less common than multiple star systems. Albireo is one of my favorites because it has a lot of really interesting information. I mean, first of all, Albireo A here is a cool red giant star, and cool stars tend to be more orange color. Blue stars tend to be hotter stars, and you can see it's a little bit fainter. This one's probably about four times the mass of the sun. The orange one's bigger. It's about 6 times the mass of the sun. And they take we're not actually sure if they're orbiting each other as doubles. They could just be what we call an optical double, where the two stars look like they're close together, but they're not actually gravitationally bound. However, these amazing stars that you can see in Cygnus, even with a pair of binoculars, you can actually resolve them on the head of the Swan constellation. They're actually, when we've pointed our telescopes at it, we've managed to find that they're actually double systems of their own. So Albireo A here, we have this satellite called Gaia, and I've got a little picture here of it. Uh, this is the Cygnus Swan constellation. You can see the two stars. A is actually two stars. AA, there's AC and there's AD. Uh, so that's kind of in order that they were discovered. And it's actually, I actually mentioned three, so I guess that's 3 stars technically. AD is a tiny star we only discovered very recently in the last 5 years. It's like about 10% of the mass of the sun. But the others are kind of this triple system orbiting here, which is quite exciting. But how do we know that these little dots are double stars? Because if you point a telescope, you're not going to make out that it's a double system because the bigger star in the system is so bright that any star orbiting nearby is going to be hidden from view. Well, there's this wonderful satellite out in space called Gaia. That's what it looks like. It's an artist's impression of it floating out in space. It was recently decommissioned, but it ran for, I think, about 10 years. And it had this great system where it would actually record the positions of stars in space. So it orbits kind of behind the Earth in this what we call the Lagrangian point, which is this point where uh, it's very gravitationally stable. It's just the right distance to have a nice stable orbit around the sun. And as the Earth goes around the sun, Gaia follows the Earth and it tracks around. And what we can do is we can take a measurement from one side of the sun, wait 6 months, and as Earth and Gaia move around to the other side, we take another measurement of that same object. And this gives us two different measurements, and we can use parallax to actually measure the distance of an object like a star. There's a limit to how far out we can. We've only mapped about 1% of the Milky Way with Gaia. Almost everything else is so far that we can no longer use parallax. But the way parallax works, if you think about it, you have two eyes and they are set apart from each other, and they allow you to have stereoscopic 3D vision. If you were to block one eye, you suddenly lose that sense of depth, that depth perception. Well, Gaia is doing the same thing, but it's using eyes that are as far apart as Earth's entire orbit. So it allows a much better depth perception. To give you an example of what kind of depth perception is, it can resolve like the width of a hair 100 kilometers away, depth perception. Our depth perception is like, I don't know, like maybe dozens of meters. So it is like a super eye floating out in space, which is really cool. This satellite's actually humongous, like a person would be a little dot standing next to it, floating out in space there. And it's mapped about 2 billion stars, creating this 3D map out in space. So we can like go onto our mapping website and see this big 3D map of where all the nearest stars are. The cool thing about Gaia and Albireo is it actually allowed us to measure, as we kind of tracked Albireo over the years, that it was wobbling slightly. This is a plot of it wobbling. So from 100 years ago until today, we've actually seen, this is its kind of motion. You can see that it's actually east-west distance is actually changing. So it's moving left, right, left, right. Now, what would cause a star to wobble in its position left to right? It's actually the fact that another star is orbiting it, and every time it circles around, this star basically is pulled on by the other star, and they both move. Even our sun wobbles as the Earth goes around it on a very small scale, but stars are much bigger, so the wobble's bigger, and we can detect it. Pretty cool, right? So, yeah, I would say that this beautiful star, this Gaia satellite had about 450 scientists working on it, and they've created this beautiful 3D map of space. So, Malcolm, I have a question for you.
I might have an answer, maybe, possibly, perhaps, perchance, I
How
think.
much money did Gaia cost?
At least $12.
You're right. Absolutely. It actually cost about $1 billion. So if
Yeah.
450 world experts spent $1 billion building this thing to create a 3D map of space, then all of them would have to be in on the flat Earth conspiracy for it to be true, and not one of them's ever spilled the beans. It's kind of it would be
You're
impressive to
you're
still
just
believe
stop.
in it at that
You're
point.
just stop. You're just
Wait,
stop.
am I proselytizing? I'm not supposed to do
You're
that on the
just
live stream. Why don't we move to another
also
target?
also just as an FYI, if anyone is not currently able to see the
I see.
stream live chat, you can refresh the page and it should come up.
All right. What's our next target for the night, Malcolm?
I think it's M5. It's the Rose Cluster.
Okay. So what we're going to do here is we're going to tell the computer to find the rose cluster. Malcolm's losing his mind
Yes,
here.
I might be a little bit.
And hopefully what we will see in the top right corner, we'll see the telescope moving around as I change targets. So let's give that a go. I typed it in the
Okay,
computer and I'm going to ask it to move.
inputting coordinates.
And you can
He's
see
he's
the
hacking into the matrix, the mainframe.
telescope is spinning and our dome is rotating. If I refresh the dome camera on the outside, you'll also see that.
Yeah.
And while it finds our new target, I have a question for you, Malcolm.
No.
The what does uh, what does the acronym TNG stand for?
You put me on the spot here, and I should know this because I've been studying it, but ironically, I don't know it.
So TNG
I
is
know what IBM stands
what you've
for.
been doing your research on, right? You've been using
Yeah, I have
TNG?
no idea what TNG stands for.
Okay,
I'm really
well,
bad at
that's
this.
all right. Now that but you are doing research on using TNG algorithm, right?
Yes,
Okay,
I am indeed
take it
using
away,
the
Malcolm.
TNG
Tell us
simulation.
all about TNG.
All right. Well, the good news is I've never actually watched a single thing related to Star Trek besides the modern movies with Chris Pine, and I probably never will.
Wait, I
Yeah.
thought you were doing TNG research. Am I lost here?
Nope. Not wrong. TNG.
Wrong
Wrong
TNG?
TNG. Yep.
Oh, wait, which TNG am I supposed to be using?
I
This
think the
one?
one you're looking at is yeah that one. That's the one. Yes,
Okay,
that one.
take it away, Malcolm. Tell
Okay.
us about
So
your
so
research.
so there's this really exciting thing. If you look at that huge big box there, it's absolutely massive. It's absolutely beautiful. We're not looking at that one. And then
No.
if you look at that one beside it, that one that's like kind of medium size, about a third of the size, it's also really cool. We're not looking at that one.
Oh,
And then if you look at that really tiny one at the very bottom, yeah, we're looking at that one.
so you just
Yeah,
look at this
sorry.
picture? That's your research?
Yeah, that's it. All my time is just spent staring straight at that little picture. That's it. That's all I do.
Right. Okay. So
Yeah.
you'll be presenting soon. What exactly do you have to show us?
I have a lot to show us, but wait, no, show you. No. Anyways, so I am working on the TNG 50 simulation, which is a nice zoomed in little simulation of the universe. And I'm specifically trying to look for these things called giant star forming clumps. Now, in our galaxy, we have these lovely nebula, and nebula, they form stars. But modern nebula are nothing at all like what I am actually looking at. I'm looking at something far bigger and far more star formy, clumpy. Yes, yes, that's the correct wording. Unfortunately, though, um, I can't show you anything right now because I think we're waiting on a picture to come up. There we go. There we go. So these are some nice galaxies from illustrious TNG. And as you can see, they all look like proper galaxies with none of those clumps. Now, clumps would look like nice little bright dots inside the galaxy. Yeah, kind of like those. And unfortunately, in the original illustrious TNG 50 simulation, there are no clumps. However, using something called IPM, which is a pancake simulation, and I'm not kidding, that is in the name, the pancake simulation. It's the intra pancake medium, but you can just call it the pancake simulation. In IPM, we actually have clumps being formed after changing, doing some little magic and changing some parameters around. We see that we are, in fact, getting clumps, which means that TNG, illustrious TNG 50, technically could create clumps if we, went in there, changed like one or two numbers, and then decided, yeah, you know what, we're just going to run this simulation again for over a year on literally tons of supercomputers. Yep.
So
Because
what
I have the
exactly
billions
are
of
you
dollars to do that.
simulating here, Malcolm? What
The
is
universe.
TNG simulating? The whole universe,
Well, yeah. So
everything?
yes, actually, it simulates it simulates a cube of space in its own universe.
That's
So it's simulating
amazing.
its own universe. Yeah.
So that
And
includes,
IPM is basically just a very, 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 very small box of TNG that is being
and by
simulated.
small you mean the size of an entire galaxy, because that's what we're looking at here, right? Like a galaxy?
Yeah, I mean it's actually three galaxies.
I see.
It's not just one.
And
So instead of
why do we
so the
want to
thing is
find
TNG.
clumps in the simulation?
Well, the biggest reason. Well, okay, so that's a good question, but the biggest reason basically is because the fact that in the real world, and by the real world I mean the real universe, in our lovely James Webb Space Telescope, we see these clumps. So of course we want to see, do we actually see them in simulations as well? They should be existing. They should be appearing. So do we see them? And the answer is sometimes, kind
Sometimes.
of,
And why would
maybe.
you want to simulate something that you see in real life?
Well, I'll let you in a little secret. Do you know how far away a lot of these galaxies are?
Uh, Very far.
Yep. Like they are so far away, it takes light over 12 billion years to get from those galaxies to us. It is that far away. So if I have a simulation, I can look at the simulation. I can look at the physics in the simulation of what's going on with that clump, how it evolves, how many stars it's forming, how massive it is. However, if I look through a telescope, I can see pretty light. Yay. That's about the extent of it.
Right. So the only
So
way to try and really figure out what's going on a time scale that we can measure is to simulate it, because we can only get a snapshot of it at one moment. And your simulation's over like millions of years, if I'm correct.
exactly, and I can watch it actually evolve
All
in
right.
time, which is even cooler.
Thanks, Malcolm. That was very interesting, and I am
You're
proud of you
welcome.
for becoming an astronomer.
That's okay.
Yes. All right. So what are we looking at here? What is this fuzzy patch? Is this as far away as another galaxy?
No,
No.
not even close. That's a thing with many things.
Astute
It has a name.
observation, Malcolm.
Yeah, I know, right?
This is
I do my
M5,
best.
the Rose
Yeah, and we're
Globular
not talking
Cluster.
about the BMW.
We're not.
Unfortunately, no.
So I kind of
Unless
gathered
that thing's
that.
powered by a V12, or is it a V10? I think it's a V10.
So
Sorry.
what is it? What makes this patch of stars so special compared to just anywhere in the night sky?
Well, a globular cluster is quite special because globular clusters like to orbit our galaxy, I think. And these globular clusters are really, really, really small, about 100 light years across, which sounds really, really, really big. But for context, our Milky Way galaxy is about 100,000 light years across. So 100 light years is it's really small. But here's where it gets cool. You got a little space about 100 light years across, and you have over 100,000 stars cramped into that little space. And that's what we're looking at right now is over 100,000 stars cramped into a tiny little space. And we call those globular clusters. And we have no idea why they
Oof.
exist.
We have no idea why they exist,
Nope.
but we see them all over in our galaxy and in other
We do.
galaxies. And
Yeah, we
globular
do.
clusters are actually really interesting because they are what I believe, if correct me if I'm wrong, that's what we first used to measure distances in our galaxies at a large scale. There were stars we found inside them called variable stars. And the interesting thing about variable stars is they basically are sending out they're changing size at a very predictable rate depending on how big the stars are. So they're getting brighter. Sorry, I said changing size. I should say changing in brightness. They're getting brighter and dimmer at a very constant rate. And there's a very interesting kind of phenomenon we started noticing is we were getting these really powerful bursts of energy from some of these globular clusters at a very high rate. Sometimes we'd get them in like at 10 milliseconds intervals. So that would be about 100 times a second. You just get this flash of light. And people didn't really know what they were. Uh, but they started calling them pulsars because it was like a pulse of light constantly hitting us. And some people thought, oh, maybe it's aliens out there because our understanding of the universe, everything seems to be disordered and chaotic. Why would you get a light shining at us from space that is doing exactly 10 flashes a second consistently for months and years on end without really varying much over time? And some of them even flash close to like 1,000 times a second. What we eventually discovered as we improved our technology and our science was that these pulsars, if I have a
Those
picture
are
of
not
one here.
pulsars.
No?
Nope.
No?
There you go. There's a pulsar. There we go.
Yeah, that's a pulsar. So it's basically a very small neutron star that's
I
spinning
love neutrons.
incredibly quickly. And it's shooting out light from its poles, just like our Earth has a north and south pole. It's got this high energy beams shooting out. And essentially, because it's rotating at a constant speed, a constant rotational velocity, you're getting that lighthouse effect, just like a lighthouse blares past you at the same speed every time if you're standing in the light beam. Well, if Earth happens to be in the direction of one of these poles and we look at them, we get this bright light shining at us that's incredibly powerful compared to most of the things we see in space. So standing out there, we're just getting blasted with this constant light. But the crazy thing about these pulsars is in order to shoot light at us 10 times a second, it means it's rotating 10 times a second. But this isn't like a tennis ball rotating. This is an entire star rotating 10 times a second. So pulsars can have the mass of like 1.5 or higher times the mass of our sun. So imagine taking our entire sun, squishing it down to the size of a city like Vancouver. I think the pulsar I was looking up earlier today is about half the distance between University of British Columbia and SFU. Like that's the entire diameter of it. But it has all the stuff in it that the sun has. That much stuff. Squished down, spinning incredibly quickly. If you think about it, the fastest people are going around our planet on the International Space Station at about 27,000 kilometers an hour. And these pulsars, if you were to stand on the edge and rotate with it, you'd be about 250 million kilometers an hour. That's about 20% the speed of light. It actually blows my mind that matter can spin that fast. That would be like the Earth spinning around its orbit multiple times a day.
I do have some really bad news for all of you, though, on the topic of if you were to stand on that star and spin with it, you'd die.
I
Yeah,
have
you'd
even
get crushed.
worse news because if you were to get into a spaceship and go fly to that star to stand on it, you'd die of old age before you got there.
No, 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 no. Not if we take into account relative. Well, wait, wait.
Yeah, I think you would. So what I've got here is a diagram of what we call ultra fast spinning pulsars. Basically, the millisecond pulsars that spin multiple times per second. Our theory is that they are actually orbiting a bigger star. And this bigger star has a disk of matter around it called an accretion disk. And this accretion disk keeps coming into the gravitational well and colliding with this pulsar and spinning it up. Imagine taking a basketball on your finger and just smacking it multiple times, and it spins faster and faster and faster. Well, the matter orbiting the big star is basically smacking the pulsar and increasing its velocity until it becomes these hyper speed pulsars. That's the theory. We're not entirely sure if that's the case, but it's one of our leading theories for why pulsars spin so quickly. So yeah, th
Spin.
that's my rant about pulsars and the Rose cluster. Do you want to switch to something that is very near and dear to your heart, Malcolm?
I do. I always want to switch to this one.
I think this is Malcolm's favorite thing in space.
No, 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 no. It's my
Oh, wait,
favorite nebula in
it's
space.
true. Your favorite thing in space is Elon Musk's car. How can I forget about that?
I think I might quit. I might just drop out here now. To be honest, I might just stop right now. Yeah, I
Well,
think I think it's worth it. After a comment like that, honestly, I think I just might quit.
I see you took that as an insult.
Yes, a little bit.
All right, so we are getting the dome to rotate to our next target. If I refresh the cameras here, you should be able to see it rotating.
Do you ever think that we could build a similar telescope using like stuff from Home Depot? I think it'd be possible if we tried hard enough.
Yeah, all you'd have to do is take all the materials, melt it down,
Yeah.
take the bulk
No,
material to a steel
no, no,
refinery,
no, 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 no,
re-refine
no,
it,
no, no,
take
no,
it to
no.
the
You're
manufacturer who
overthinking
makes the
this.
telescope in the first place,
You're
and then just tell
overthinking
them,
this.
here's the raw
You
materials, make the
are
telescope.
you're overthinking it. You're overthinking it.
Okay,
I think you're
how are
just
we?
overthinking this.
Then,
Listen, 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 listen.
okay, I'm
All
listening.
I'm saying is we could 100% make a superconductor with stuff from like Home Depot. And if we could do that, then we could 100% make a multi-million dollar telescope from stuff from Home Depot. I'm just saying. I'm just saying.
All right,
I have I
you get
have good
right on
faith.
that, Malcolm. You get right on that
You
target.
know
So,
what? I will.
what I've got here, we got our color camera pointing at the telescope. So this is actually real live stacking of the object as it is visible right now. Now, when I say live stacking, if you look in well, I don't know if you guys can see it right now, but yeah, you can see it. In the bottom corner here, this little frame bar is going up. We're taking a 20-second long exposure, and then what we're doing is we're laying the exposures on top of each other. Well, we're trying to. Just drop the last exposure. I might have to turn the line frames
You
off.
can probably decrease the black level a little bit there.
Yeah, you're right. You're right. What I'm going to do is try and make it more visible.
Yes, there we go.
So tell me about this
No, no, that's
object,
fine.
Malcolm. Why is this your favorite?
Well, okay, so kind of a little bit of background information. In space, which we are looking at, there are two main types of nebula. There are planetary nebula, which are terribly named, and there are stellar nebula, which are better named. The thing is that stellar nebula, for the most part, when you think of a stellar nebula, you think of something like the Eagle Nebula or the Pillars of Life or the Horsehead Nebula. You think of all those beautiful colors, the rainbow, but you never think of a nebula as just being an ice white or blue color. And that's something that this nebula has very unique about it. This nebula is very whitish blue in color. And the reason is that unlike a lot of those other nebula, which are a bunch of gas emitting all these colors, this particular nebula is a reflection nebula. Now, what that means is the gas is actually reflecting light from that central star out towards us. And that's why we're seeing it all, well, white like that. Now, this star is actually thought of as possibly being another one of those binary star systems that Kieran was talking about. But that central star is super duper bright. And that's why we're seeing it like lighting up all that gas like that.
That's incredible. Um, then so was that star born from that gas possibly? Is that why it's in there, or did it kind of the gas just kind of drift into where the star came is? Do we know?
I believe it was born in there. There's two main ways you would have a stellar nebula like this. One of them is, of course, like this, where it's the stars being born inside the area of gas. And then the other one is oftentimes you can have supernova remnants, but I do not believe that this one is a supernova remnant. So I believe this is a star that was either formed in it or is a star that's just behind the actual gassy area. But I believe it's the stars inside the gassy area and it was formed in it. So these stellar nebulas are also called stellar nurseries. And these are areas where there's a lot of gas that are producing many stars. In this case, it's like one, but yes,
Well,
semantics.
one that we can see at the moment. It could be two if they're
Yes, the one
orbiting
we
each
can see.
other.
That's true. That's true. And I mean, it would also take us, you know, 1,300 years before the light from today reached us. So it's going to take a little while,
So if
unfortunately.
most do most stars form in big clouds of gas like this?
No, yes, they do. In fact, they have to. Well, not necessarily in these big clouds of gas like this, but yes, they have to form inside these gas because what's happening is the gas is over time you have like this area where the gas is higher in density, and so it starts to compact because of the gravity, even if it is a low amount of gravity. The gravity over time starts to actually bring all the gas together, and that's how you end up with those stars being formed. If you don't have any gas or you don't have a high enough density of gas, you can't have stars forming.
So stars are made
So
out of
you do
gas.
need. Oh yes, stars are very
So
much so made out of gas.
then I don't know if I trust you, Malcolm. I don't know if this story adds
Oh,
up.
okay. Well,
Like,
guess I'll just leave.
if stars form in gas, why, when I look up, is there not the big ball of gas that the sun formed from? Why don't I see all that gas? In fact, why don't I see a bubble of gas like this around every single star I look at in space? Where'd the gas go? Did it all go into the star here?
It went into the star.
All
I
of
mean,
it?
okay. So
100% of the
there's a couple
gas?
things. No, not all of it. So for something like our sun, there's a couple of things that would result in our sun not having gas all around us. First off, we wouldn't be able to see any of that gas because it would be way too diffuse in terms of the actual light. So
Uh-huh.
we wouldn't actually be, if we were actually in one of those nebulas, you wouldn't actually really see much of the nebula at all. You have to be a certain distance away to actually see the nebula. So that's the first thing. The second thing is a lot of the times, it doesn't necessarily mean that there is a huge area of gas like this one, where there's like a lot of gas that can be lit up. doesn't stars to form don't necessarily need to be in one of those big nebulas. They just need an overdensity of gas in regions of the galaxy. However, there's more stars, higher density of stars form in stellar nebula like this. Now, for something like a lot of these stars, what also ends up happening is A, the star does use up that gas. And as you have more stars forming in the area, more of that gas will be used up. The other thing is, though, is that from stellar formation, you do end up with photon pressure and you end up with stellar winds that blow away that gas,
Yeah, I think I
which are
remember
some
reading that
problems.
only about 10% of these gas clouds end up as stars, and then once the stars reach a certain size and there's enough of them, the light, the photons, and the other well, I guess it's all photons, the radiation that they emit actually pushes the gas away. So most of the gas just gets
Oh, yeah.
blown away. It's called radiation
Yep.
pressure.
Yep. Got to
Sorry,
be
I might have
careful about
broken
that.
up a bit there. That might actually be one of the reasons why galaxies, as they get older, go through this process called quenching, where they stop forming as many stars because the gas is pushed away. Over time, all these gas clouds disperse because all the stars form. One of the methods of quenching that is postulated. There are others. But we've talked enough about your favorite target, Malcolm. I know you could stare at it all night, that beautiful blue.
I could. I could.
But let's look at a different kind of nebula of a different sort of shape. So let me see what it's called in the catalog. NGC 6826.
Six. Yep.
Hey, it worked.
I know, I know. We have some wonderful names for objects. My one of my personal favorite stars is beautifully named R136A1. Absolutely magnificent name, by the way. Just so beautiful. So beautiful.
All right, we got to wait 20 seconds here for a new frame to start because the previous frame I think had some motion in it. Yep, did you see that for a second? That was not comets. We are not under attack from aliens or a giant comet fall.
Yeah.
Those were just stars moving past the field of view.
I mean, hey, you never know. Could have
Well,
been.
you never
What if
know.
it was?
Actually, I'm scared now. I'm not
Yeah.
going to go look outside. Just to be safe, I'm
No,
going to
don't look
stay
outside.
inside.
Just yeah, just stay inside.
All
Gotta be
right,
safe.
our first
Oh, look, a
shot
satellite.
has a satellite going through. Thank you, Elon. Let's clear it and try again. Big old
I think you
Starlink
may have
satellite.
to you may have to lower the time on this. It's very bright. It's a very bright object.
It is. Let's go to 10
Yeah,
seconds. Why
we gotta
not?
be
Let's
careful.
just
We gotta be
have it.
careful.
So if we expose too
Let's see if that
long,
works.
our little camera gets overexposed. You've all experienced that if you're pointing a camera at a dark space and then suddenly go to a bright space. What do you think? A bit less? Or should we just
Yeah, I
play
can
with
do a
the
little less.
levels?
I think you can do. Oh, careful, careful. We don't wanna kill too much of it. I think you can go a bit
Let's
less.
do a
I
bit
think you can go a bit
less.
less.
Because it will
What kind
stack.
of gases were in that white nebula? Wondering what elements. Well, here's the safest thing to think. I mean, I think a lot of it there is suggestions that there's hydrocarbons, but um, the safest bet when you look at a nebula that isn't one of these planetary nebulas, when you look at a nebula, the safest bet is hydrogen because about 95% of the visible matter in the universe is hydrogen, just hydrogen. It's all hydrogen.
Now, normally hydrogen glows in pink, but this one isn't glowing as in it's being excited and it's now emitting its own light. It's just reflecting the blue light off the star, which is why it looks blue.
Exactly.
So pretty much no matter
Yep.
what gas you got there, it's gonna look blue because the dominant light source is the reflected light of that core star. Speaking of little stars, are we looking at a little star now? This
We
is
kind of
the
are, yeah.
blinking planetary nebula.
Yeah. So the blinking planetary nebula. Now, we'll get into why it's called that, but first we kind of should talk about what kind of nebula this is. This is a planetary nebula. So named a planetary nebula because it's coming from a star. No, I'm kidding. That's not reason why. It's actually because when we first saw them in space, we thought they were planets, but
Well, can I
they
do a
aren't.
minor histographical correction there? The
Histographically.
first recorded writing of planetary nebula. See, we're nerds here, so we have to correct each other and be all, smarmy about it. It's kind of our job. Uh, Technically, he
Actually,
wrote it's planet-like. He did not say I think it's a planet.
oh, my
And
apologies.
then
My
and then
apologies.
from then
It's
on, they called
planet-like,
them
yes.
planetary nebulosities. They look like a faded
Yeah.
planet. But the reason they thought that is because their telescopes sucked back then, and you couldn't really tell the much difference between one smudgy fuzzy thing and another smudgy fuzzy thing. So everything was just a
Yes.
planetary nebula. Consider yourself
So,
well and chastised, Malcolm.
oh my gosh. So, anyways, before I was rudely interrupted, this nebula is a planetary nebula. This is what happens when a star dies and doesn't explode into a magnificent supernova. This is what happens when a star simply says, you know what? I think I'm good. I think I'm just going to stop here. And it ejects a ton of its material out, and it becomes what's known as a white dwarf, which is what we're seeing in the center. There's that bright little star in the center is a white dwarf. And a white dwarf is kind of just I think it's about the size of Earth or Mars. I think it's about the size of a white dwarf. And it's dead. It's just a really big hot rock. So imagine Earth if it were really hot. Yeah, that's the best way to describe it.
It's a pretty good description.
Um, yeah, I think so too. And the actual nebula itself is kind of cool here. So this one is called the Blinking Planetary Nebula for two reasons. So one, what we can't really see here is that on the edges of this nebula, there are these two little red, well, they kind of look like jets. And these are known as flyers.
You can actually see the little lighter bits on the edges if you look closely, and I
Yes,
can
you can.
actually
You
see a
can.
tiny bit of red at the bottom, though you guys might not be able to see it on the stream.
It's hard to see.
Yeah,
But these flyers, they're basically just charged atoms that are moving outwards at supersonic speeds away from the center of the central star.
just like my pulsar, they're moving from the poles.
So they kind of look like the whole nebula itself ends up kind of looking like a bloodshot eye. Okay, so you have a bloodshot eye, but why is it called the blinking nebula? The cool thing about this nebula is actually that when you actually view this nebula, not through something like this, when you view it through a small telescope with your eyeball, if you were to look directly at it, the only thing you would see is the central star because it's overwhelmingly bright. However, if you were to look to the side a little bit, what you would be able to see is the green cloud that surrounds it. So if you were to move your eye back and forth across the eyepiece, it would appear to be blinking. Hence the name. Sometimes we have some pretty creative names. Other times, we don't. Fortunately, this is one of those times where we did.
Oh, I thought it was just like an angry British man who was like, that blinking nebula.
No,
No? Why did everyone
no.
leave the room? Why am I alone on the stage at the comedy night?
Uh-huh.
All
We
right.
do have about 5 minutes left in the, I was about to say in the simulation, but that's not correct. 5 minutes left in the presentation.
Should we do a
So
galaxy then?
Kieran, I think we should do a galaxy. I think we should do the galaxy. I think we should do your favorite galaxy.
My favorite
Just,
galaxy? But then we're going to be here
yeah,
for
just be
another
careful.
hour.
I know. Be careful because he'll go on and on and on and on.
Well, I
I think,
let you look at the Irish
are we
nebula.
moving to, that's true. You did let me look at the Irish
Okay,
Nebula.
we're switching to M51, that's the Messier catalog. NGC 5194 is the National Galactic Catalog. It's the same object though. It's much easier to remember if you just think of it as the Whirlpool Galaxy.
I think that's a better name.
Yeah, I think we should just get rid of all these numbers. They don't serve anyone.
I agree. Honestly, I agree. Yeah, they like who are these for? Scientists? Nah, we don't need those. I think potentially.
Well, I kind of like my cell phone, and it's because of science that I have it, so. All right,
Yes.
hopefully we have got it on now, so I'm going to clear the old stacks and start new stacks. Now this object's quite faint. So, oh, never mind. It showed up almost immediately. Let's see if
Oh
we can
yes,
zoom in on
faint.
the whole thing. Just gonna adjust some of the colors here so we can get a more.
Oh, well, you're only doing a 5-second exposure, which does not help.
Yeah, you're right. What should we do?
Yeah.
20?
Oh, do 20. Go 20. Go
We'll do
20.
20.
Go
We'll just
20.
stack it on top of the other
Go for the
frames.
go for the big numbers. This is a big thing. It needs the big numbers.
Yeah, and it's very faint. And I actually see a second thing over here. It looks like it has a buddy, which is why I love to talk about this one. But let's wait for this 20
So
second
which
frame
one
to
are you?
finish.
I'm the big galaxy. You get to be the small galaxy.
I'm the little spoon.
Oh,
All
well,
right.
I am not part of this conversation anymore. I am.
Well, I had to get you to stop somehow. Okay, here we go. So if we look here, we can see two galaxies. And I tricked you. I said the Whirlpool Galaxy, but I lied. It's actually the Whirlpool Galaxy and NGC 5195. And if you look here, you see this dark band coming out of
Good names,
5195.
man. Good
Oh, I
names.
know. We should call it the Little Spoon. That's what I think we should call it from now on. Just gonna adjust this color a bit. Ooh, that's way too green, isn't it? Okay. See if we can make it resolve a bit better.
Oh, look at that.
Ah,
Nice and
now
pretty.
as we get more stacks, you're going to see more and more detail. So it's my job to entertain you until that happens. If you see this dark band here, this is what we call a plume. And it's actually matter that's being exchanged by these two galaxies. They're so close to each other that they're actually exchanging matter with each other, which is pretty awesome, right? This galaxy is about 31 million light years away, and this span here is about 80,000 light years across. So we think it's about 80% the size of our galaxy, the Milky Way. Of course, we don't know the exact size of our Milky Way. It could be, like Malcolm said, 100,000 light years across. It could be 200,000. It's somewhere in that ballpark. So going with the 100,000 figure, this is about 80% the size of our Milky Way, but it's only about 10% of the mass. So even though it's very spread out, it's not nearly as dense as our galaxy. And the poor guy barely has any mass to spread, and this other little guy comes along and steals a whole bunch of it. Well, actually, they're kind of exchanging matter, so it probably evens out in the end. But if you look
I
here,
guess it doesn't matter. Ha 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 ha. Why is no one laughing?
yeah, why is the stage empty? Like you're the only one in the comedy club. Okay,
All right.
so what we've got here is this plume of matter being pulled in from one galaxy to the other and vice versa via gravity. And what these galaxies are actually doing is colliding, but very, very slowly. And why I love to talk about this is it's almost a glimpse of our future because we think that the nearest galaxy to us, Andromeda, will one day collide with our own galaxy. And I even found an image from NASA where they show that. So, ooh, maybe that's too big. Let me try that. Okay. So if you look here, you can actually see this is the Triangulum galaxy. It's just another nearby big galaxy. We can ignore the green line. Just look at the red line and the blue line. The blue line represents our galaxy, the Milky Way, and the red line represents Andromeda, the closest galaxy to us. And this is a prediction of what's going to happen in about 5 billion years' time. So this arrow here represents about 2.5 billion years time from now. They'll be closer together, but they're moving towards us, hurtling towards each other at, I think it's like 200 kilometers a second. Don't quote me on that. And in about 5 billion
I'm
years, they'll
quoting
be
you
in
on
the
that.
position where this X is, and you can see they starting to gravitationally interfere with each other in a big way. What basically happens when two galaxies collide is they sort of merge over time. Sometimes they might be going so quickly that they pass through each other like a cloud. And so this is a simulation also from NASA to show what happens when two galaxies collide. And it's like two clouds kind of slowly bouncing through each other and then coming back a few times, swinging like a rubber band until they merge into one mega galaxy. Now, this looks very violent and explosive, but it actually takes billions of years. So imagine watching a car crash, but the cars only move 1 centimeter every
That's
10,000
a
years.
that's a
You
that's a horrible, horrible.
And now, yeah, I
It's
love
a
that
horrible
analogy.
comparison.
So that's what we're seeing here. We're seeing a car crash where they move so slowly that you just can't see anything happening in real time. So instead of, even though galaxies are absolutely humongous, we're not getting this violent collision where stars crash into each other and solar systems are torn apart and Malcolm goes flying out of the observatory. None of that. Oh, because I'm going to hold on to something because I know it's coming.
How are you?
Yes.
Are
So,
you?
so what's going to happen here is stars, because they're so far apart, they're essentially just going to pass through each other like these two stars in my slideshow here. They, there's way more empty space than there are stars. So as the stars fly past each other, they pretty much never crash into each other. It would be like if Malcolm stood on one side of a football field and I stood on the other side. We each had a marble in our hand and we threw the marbles at each other. Do you think it would be easy for us to get those marbles to collide in midair? It'd be
I could do
very
it.
difficult.
No, I could do it.
Yeah, we could do it if we had like a year. But the thing is, stars
Yes,
are
I could
like
try.
two marbles and 200 football fields apart. They even though these galaxies are interacting with each other gravitationally, they're not physically colliding. Stars aren't. Gas and dust might, but the stars fly past each other. It would be like watching two clouds in the sky pass through each other. It's not violence, it's just the slow merging. And so what would happen if Andromeda hit a solar system like ours in our galaxy is even our solar system likely wouldn't be disrupted by a passing star. We would just slowly change our whole solar system's trajectory until we start orbiting the combined center of mass of the two galaxies. So the future of the Milky Way and Andromeda is just another super galaxy. What do we call it? Milkdromeda? I think that might actually be the official
I am
name.
not calling it Milkdromeda.
I
No.
think that's I think
Call it
someone
Andromeda Way.
I think someone with a
Andromeda Way
PhD
is
already
better.
coined it that, so I think if we're
No.
just stuck with that forever. Yeah,
No, I will. I'll have my own head cannon.
we already got something to be ashamed of. We're gonna meet aliens one day, and they're gonna be like, "We come from the Vega Saturn X galaxy. Where do you come from?" We'll just hang our shoulders and be like, "The Milky Way," and then they'll laugh at us. We could have
Why is
come
that
up with a
bad?
cooler
That's kind of a
name.
cool name. What
Milky
do you mean?
Way? Really?
It literally looks like a big stream of milk
Okay,
above it. That's what it
I got
looks
a
like.
question for you. How many planets have mammals on them?
At
One.
least one.
So our galaxy is literally called Mammalian Bovine Secretion Way. Like that's not cool, man. I'm sorry to say.
Why do you know that?
What do you mean? Why do I know that? It's just common deduction.
No, but why do you know that's what the? Oh, never mind.
All right.
I know what you're
Well,
getting at. I know what you're getting at
it's
now.
past 11, and I think we hit most of our favorite targets. Thank you, everyone, for tuning in tonight. Do you have any closing notes, Malcolm?
Yes.
Go for it.
Team Andromeda Way all the way.
Andromeda Way. Milkdromeda is definitely my
Nope.
team.
No,
So,
no, 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 no. Definitely not.
we should get a vote going in the
Andromeda
chat.
Way will win. No, don't get a vote. Ah,
All right. Thank you, everyone, for tuning in to Starry Nights Live. It was lovely to talk to you all. I apologize for the technical difficulties at the beginning. I'd like to thank our moderators, Zena and Abby, as well as Joanna for helping us deal with our technical difficulties and setting up a new stream for us, and just for being
thanks, Joanna.
our mentor and astronomer and all around person to look up to.
Wait, if I get Joanna to be on Team Andromeda Way and she has a PhD in astrophysics, does that mean I win?
Yes, but I don't think she would sink that
Awesome.
low because it's already named. All right.
Ah,
Everyone,
you're hurting my feelings.
have a good night, and remember,